All right, so today we're talking about something called upper and lower bounds. And basically, what we've come up with so far is you can make a scatter plot, you can draw a fitted line, but it's not going to be perfect. There's always going to be some values that are a little higher and some values that are a little lower. And upper and lower bounds are going to give us some cutoffs that say all of the data should fall within a certain range. And we're going to use the scatter plot and graphing to sort of determine where that range is. All right, so we're going to look at some data from 1997. An anthropologist discovered an early humanoid in Europe. As part of the analysis of the specimen, the anthropologist needed to determine the approximate length of the humanoid. The skeletal remains were highly limited, with only an ulna bone from the forearm being complete. The bone measured 26.4 centimeters in length. Now, not something we need at the moment, but we will need that piece of data in the future. Your task, consider how you would determine how tall the humanoid was. What process would you use? So first, we have some data that's been gathered over time for forearm length and overall height. So this is data that's already been collected. And we can see 1, 2, 3, 4, 5, 6, 7, 8. So there must have been 8 skeletal remains that they were able to find both the overall height and the forearm length. So things we would need to do, we would want to plot the data in a scatter plot. We would want to draw a line of best fit. We'd want to write the equation for that line of best fit. Line of best fit. Looks like Lord of the Rings almost to me, sorry. And last, we'd want to substitute our value in for X. And that way we would be able to find our height prediction. So what I have here is my scatter plot where I have plotted just the 8 points from the table. And then you can see that I put in a height range over here on the left. 140 was my lowest because I knew I needed a number between 140 and 145. I counted by fives because that was the biggest range that I could have and still get to the 185 that I needed at the top. And on the bottom, each box is worth 1. So 21, then 22 is labeled. 23, then 24 is labeled. 25, then 26 is labeled. So I plotted my 8 points, and they're sort of the darker, larger dots. And then I used a ruler, and I drew what I considered a decent fitted line. There were 8 points. So I have 1, 2, 3, 4 with positive residuals. 1, 2, 3, 4 with negative residuals. Also means 4 above the line, 4 below the line. Followed the pattern of the dots the best that I could. Does not need to aim for the origin. In this case, it looks like it's aiming for the origin, but you'll notice that there are 2 breaks. And then I pick 2 points that are actually on my fitted line. So if you're somebody that's going to do this one alone and get your own set of data, you'd want to pause the video here, plot your 8 points and draw your own fitted line and pick 2 points on your fitted line, because these 2 points on the fitted line did not come from the data set. They are there because they were good on my fitted line. All right, so I need to find, first, plot the data on the scatter plot. We've done that. Draw the line of best fit. I've done that. Write an equation for the line of best fit. So I'm going to take the 2 points I have there and do y2 minus y1 over x2 minus x1. And I got 20 over 4, which is a slope of 5. So that's pretty nice. That's workable. Y equals 5x plus b is what I would have so far on my equation because I have the slope. I would pick one of the 2 points. I'll use 23, 149 just because it's smaller numbers, but not going to change the answer. I'm going to solve for b. So I'm going to have 149 equals 115, not 114, plus b, and subtract 115 from both sides and get that my b value for my fitted line that is on your screen right now is 34. So I'd say y equals 5x plus 34 is my equation. Last, substitute our value in for x. So we're saying that the bone that we found had a length of 26.4. Forearm length was the X value. That was the thing that we had control over because that was the thing we found. And then we were using that control variable to find the dependent variable, the height. So we're going to plug it in for x. Y equals 5 times 26.4 plus our y-intercept of 34. And we would have 132 plus 34, giving us a prediction that this person whose skeleton we found is actually 166 centimeters tall. If we describe the correlation, we notice that it is pointing in a positive direction, but they are certainly not lined up. So again, this would fall under probably moderate. And it does look like they are pointing in a line and not making some sort of curve. So we would say moderate, linear, positive correlation. And these are all shortened, right? Mod for moderate, linear, positive, and then correlation. Draw a fitted line and write an equation, identify the variables, show your work algebraically above. We did that. We got y equaled 5x plus 34 as our equation. Interpret the meaning of the slope and y-intercept. And people always struggle with this one. Our slope is 34. So that means, I'm sorry, I apologize. Our slope is not 34. Our y-intercept is 34. So we're saying 34 is the y-intercept. So if you have a forearm length of 0, you are 34 centimeters tall, and that does not seem reasonable. This would fall under the category of does not extend that far. We cannot continue our data that low into the graph because it's so far away from the points that we've collected. But we can do the slope. And the slope would be for every 1 centimeter of ulna length, the human should be 5 centimeters taller. So it's a 5 over 1. So slope is 5 over 1. So that's your rise over your run. That's your y-axis over your x-axis, which makes it height over length. And so we're saying for every 5 centimeters in height, we have 1 centimeter in forearm length. That's where we're getting those numbers from. All right. And we said that the y-intercept does not make sense in this context. Just can't extend that far down. And I noticed that I skipped this question we had already answered. Show your work to predict the height of the early humanoid. We got 166 centimeters. So does, of course, I just answered the question that's right below it. Does the y-intercept make sense in the context of this problem? No. A 34 centimeter height does not have a 0 centimeter ulna. Just figured I'd get ahead of the game on that one, I guess. All right. Because the height you found for the humanoid is a prediction, the actual height of the early humanoid was probably a little shorter or a little taller. In this problem, you'll investigate how you can report a range of values for your prediction of the humanoid's height. So everything we did on the front, review from 411 and 412. Look at the data you collected and the line that models the data. Identify the point that is farthest from the line you drew. Now, very, very important, farthest from the line you drew, and you're always going directly above or directly below. So what is the point that is the furthest away, either straight up from the fitted line or straight down from the fitted line? And you'll notice like this one over here is almost 2 full squares away, right? Almost 2 full squares away below the fitted line. This one is a good contender here. It is about 2, but this one right here is just over 2. That one is actually our max residual. And so we would go with, that point is 24,165. All right, so that one is called our maximum residual. It is the furthest point, either directly above or directly below. And we would put in like those little dashes. So not a solid line because it's not actually a line. It's just a distance that we're going to measure. So we're going to say that the point that is the farthest from the line we drew is 24,165. That point's going to be our max residual. Calculate the residual for this point and show your work algebraically. Okay, so we're going to use our fitted line, which was y equals 5x plus 34. And we're going to say, what is the y value if we plug in 24 for x? We're going to do 5 times 24, which is 120, plus 34. We were predicting that we should have gotten 154 as an outcome, and we got 165. So actual minus predicted. Wow, my handwriting is awful there. I apologize. That is supposed to say predicted. Would be 165, take away 154, giving you a residual of 11 centimeters. So the actual is 11 centimeters off from the predicted. It is 11 longer, or 11 taller, I should say, than we predicted it would be. In a different color, draw a dashed line that goes through the maximum residual point and is parallel to the line of your model. All right, so we're going to go back here. And this is one where you're going to need a ruler, and you're going to need a steady hand and a good eye. And you're going to go in purposefully to draw a line that is parallel. So you want to look and see, is it at the same angle as your fitted line? And I just sort of like twist mine and move mine a little bit until I feel like it looks like it's parallel. And I'm going through that highest point there. And that dashed line is called my upper bound. It's the upper boundary. We're saying there should be no dots higher than that dashed line. You're also going to do another one on the other side. Now, what you're going to notice is that you are not picking one of these points that's down here. You're not picking another point that was from the data set. You're saying the dot that I picked as being the maximum residual was 11 above. So now I need to go 11 below. So 11 below that point will be right about here. And so 11, so same thing, I'm just going in the other direction. I'm trying to go down by 11, so it should be the same distance away from my fitted line. I am looking again to make it parallel. And you'll notice that it's lower than this dot, and that's what it should be because we said this one was the furthest away. So you'll notice that this dot is a little bit higher, and that's a good thing. That means we picked the correct maximum residual, and I'm just trying to make sure that I get parallel here. Looks pretty good. And if you picked the maximum residual, all of your points should be in between those two dashed lines. So one is 11 above, one is 11 below. So they are the same distance away from the fitted line, and they are parallel to the fitted line. This one called your lower bound because it is the lower boundary. All of the dots should fall on that line or closer to the fitted line. All of the points should fit on the upper boundary line or closer to the fitted line. So in between those two dashed lines. And they gave you a model here. The same idea. This one had a slightly different looking slope because they had different scale on the y-axis on theirs. Using the upper and lower bounds that you just drew, create a range of values for the possible height of a humanoid with a forearm length of 26.4 centimeters and show your work below. So we're saying that the prediction, we're saying that, let me just make sure I've got the right one. We are saying that it was a 154 was the prediction on the fitted line, but we were admitting that we might have been off by as much as 11, right? Because it could have been up as high as 165. That means we might have been off by as much as 11 on the lower end as well. So you might have had a point that was as low as 24,143 or as high as 24,165. That means you could either have been under by 11 or over by 11. And if you subtract them, that means there was a 22 centimeter range, which makes sense, right? Plus 11 minus 11 would be a spread of 22. So all I did was take the predicted 154 and go 11 above it, 11 below it. Now, the other thing that you can do is you can do the same thing with the equations. If our fitted line equation was y equals 5x plus 34, and we're saying, oh, but it might have been 11 higher. Okay, so if I raise this by 11, our upper bound might have been y equals 5x plus 45, which would be 11 higher. Our lower bound might have been 11 lower, y equals 5x plus 23. So this would be the equation for the upper boundary. This would be the equation for the lower boundary. And if you plugged in 24 to each of those, you would get the 143 and the 165. All right, I think height of the prediction needs to be within 11. All right, so 166. Okay, so the last piece that I need to wrap up on that is if our humanoid prediction was 166, if we predicted our humanoid was 166 centimeters, they may have actually been 11 higher or 11 lower. So they may have actually been 177 or as low as 155 if we had been off by that 11 range. All right. Last piece. Reflect on the bounds of the data. Was your model useful for predicting the humanoid? We would probably say no. And you're like, come on, why do we do all this work if you're going to say no, Mrs. Fraser? A range of 22 centimeters is huge. So a range of 22 centimeters is too much of a spread. And I'll tell you why. If somebody had been in a store and they had been off by the height of 22 centimeters for, say, the person who had robbed the store. 22 centimeters, if you look at your paper here, is just a little bit wider than the paper. You're saying that it is acceptable to be wrong by as much as 8.5 or 8.75 inches. So if a person robbed a store and I said, oh, I think the guy was like 5'4", but they were really 6 feet tall, that's too far off. So a range of 22 centimeters is too much of a spread. So is it reliable? Not really. We collected data that was just too spread out to give us a reliable prediction. However, that is something to recognize when you're thinking about real world. Some of the data that you collect may provide an equation that is not useful because it's just too broad. And that's the case here, where a 22 centimeter range, it's just too much. You can't be off by almost 9 inches and think that that's reasonable. So I'm sure we'll have lots of questions. I love this stuff on upper and lower bounds because I feel like it's really satisfying when you get the picture done and you've got these two parallel lines on either side of your fitted line. They should be equal. One should always be the same amount above as below. So they have this symmetry to them that's really satisfying. And hopefully we can talk about it in class with any questions that you have. Thanks, guys.